All right, now we're going to talk about something called the ideal gas law. And the ideal gas law is an equation that combines all three of the gas laws that we just talked about into one equation. It is said that this equation describes an ideal gas, or a gas that behaves ideally. Now, really, this is a hypothetical gas, okay? No gas on the, well, okay, let me rephrase that. This is a hypothetical gas. Several gases actually do follow along and behave along the ideal gas law at normal temperatures and pressures. When we're at low temperature, low pressure, atmospheric pressure, stuff like that, ideal gas law is a little bit easier for gases to follow. When we get higher up into the temperature spectrum, or we get higher up into the pressure spectrum, the math gets a little bit wonky and gases tend to deviate further from ideal gas law. So this is a really good approximation for us when we're at conditions that aren't extreme. But when we start cranking up the temperature and the pressure, the conditions change. Ideal gas law tends to fall apart. Okay, what happens with ideal gas law, or the equation that we're going to use, is going to be PV is equal to NR times T. So it's pressure times volume is going to equal N, which is the number of moles of a gas. R is our universal gas constant, and T is our temperature in Kelvin. And so I did not tell you pressure units for a reason. Okay, so that was not an omission on my part. That was actually something that was sort of thought about. And so you get to pick which R value you use based on the pressure unit that you're given. Okay. And so if you're using atmospheres as the pressure unit, or your pressure is given to you in atmospheres, you're going to use an R value in this equation of 0.08206 liters times atmospheres divided by mole times K. Okay, so 0.08206. If you're going to use your pressure in pascals, the pressure that comes to you in a Pascal unit, and you didn't want to convert it to atmospheres, the R value that you would use would be 8.314. 8.314 meters cubed pascals divided by moles times K. And if your pressure was given to you in torr, and you were absolutely dead set on doing the calculation in torr, your R value for that would be 62.36. 62.36 liters times torr divided by mole times K. Okay, and so that's how we end up working with that stuff. So here we go. So suppose we had 1.000 moles of a gas at 1 atmosphere of pressure and at a temperature of 0 degrees Celsius. What would we have to find our volume? And so what's the volume? So volume equals question mark. Okay, well, we're going to use PV equals nRT, but here we're going to rearrange it so that we can get the volume alone. So if I have PV equals nRT, I'm going to take my pressure, I'm going to divide this side by pressure. I'm going to cancel off my pressure units because they're the same. And then I'm going to divide this side by pressure, because what I do to one equation, I have to do to one side of the equation, I have to do to the other side. And so in this situation, my volume is going to equal nRT divided by my pressure unit. Okay, so let's just put our pieces in, and unfortunately I wrote it a little low, so I'm going to do a weird diagonal equal sign to get me up a little bit above out of this space. So we have 1.00 moles. So here we go. 1.000 mole. Boom. That's going to get multiplied by R. Okay, so which R am I going to use? Well, I see that I have atmospheres, so we're going to use this 0.08206 liters times atmospheres divided by mole times K. And then we're going to multiply that by the temperature, which we have 0 degrees Celsius. Now 0 plus 273.15 is 273.15. 273.15 K. And we're going to divide that whole mess by the pressure of 1 atmosphere. Okay. Now, when we start talking about canceling off units, we hope that when this is all said and done, we end up with a unit of volume in the end. So we want to get liters to be all alone in the top when we're done. And if that happens, then we set it up right. So moles are in the denominator, or the numerator of the numerator. Moles here are in the denominator of the numerator, so that moles cancels. Okay. Kelvin, same thing. That Kelvin cancels. Atmospheres up top are in the numerator of the numerator, and I'm in the denominator here, so those cancel off. Look at that. Liters is by itself up in the top, so we set it up right. Now we do the math on this. 1 times 0.0826 times 273 divided by 1. We're going to end up with a number that should be pretty darn close to 22.41 liters. Okay. Now, this 22.41 liters, that is an important number for us. And that important number represents the volume of an ideal gas under what are known as standard temperature and pressure units, which is what we have right now. And so standard temperature and pressure otherwise known as STP. And so that is when we have 0 degrees Celsius, 1 atmosphere of pressure, we get this 22.41 liters of volume. Okay, so ideal gases, or gases that follow the ideal gas law or are behaving ideally, will have a volume of 22.41 liters if there is 1 mole of it at 0 degrees Celsius and 1 atmosphere of pressure. And so that is a conversion that we can use if we know that we are at STP, because it saves things. It saves us some time, is essentially what we got going on with that. So now, here's an example of how to use ideal gas law given a word problem or a story problem. And so this also is something that we're going to see and we're going to do. So our example here is calcium carbonate is decomposing via the following reactions. So calcium carbonate is a solid. We heat it up, it turns into calcium oxide, a solid, and it releases carbon dioxide gas. So that's that. If the CO2 is collected in a 250 milliliter flask, and after the collection it has a pressure of 1.3 atmospheres and a temperature of 31 degrees C, how many moles of gas were collected? Okay, so we're going to use ideal gas law. So PV equals nRT. Now, we want moles by itself. And so we want to divide both sides by RT to get moles by themselves. And so when we do that, we end up with N is going to equal pressure times volume divided by R times T. Okay, so that's what we're going to start putting our pieces in. If we look at what we have and what we don't have, let's look at our numbers. Now, first thing I'm going to look at is that my atmospheres is my pressure. So that means that we're going to use an R value. So our R value is going to be 0.08206 liters atmospheres mole K. Okay, so first thing I'm going to look at is my volume is in liters with this R unit. So that means that I have to take 250 milliliters, and we have to turn that into liters. So let's do that first, all right? So 250 milliliters over 1. Now we know that there are 1,000 milliliters in 1 liter, which means that we're going to have 0.250 liters, okay? So that's one thing that we don't have to calculate. Our temperature is given to us in Celsius. So 31 degrees Celsius has to go into Kelvin. To do that, we add 273.15 K, and the value that I get for that is 304.15 K. Okay, so now we have volume correctly, we have a temperature correctly, we had the pressure unit already, and we know the R value already. So we have the numbers converted, so all we got to do is put it into the equation and do our math. So pressure is 1.3 atmospheres, 1.3 ATM times our volume, which was right here, which is 0.25 liters. So that's that. We're going to divide that by R times, so 0.08206 liters atmospheres divided by mole times K. That's going to get multiplied by our temperature in Kelvin, which is 304.15 K. Make my line a little bigger. Okay, now K cancels K. Liters cancels liters. Atmospheres cancels atmospheres. And because moles are in the denominator of the denominator, when we do the math on it, the unit of moles actually will end up in the top, which is what we want because we're solving for moles here. So we set it up right. So that's cool. We did the math right, or the setup right. Now all we got to do is just plug it into our calculator and get a value. 1.3 times 0.250. Enter, divide that by 0.0826 times 304.15. And so that gives me a value of, where are you? 0.0 moles of carbon dioxide gas. And so that is a very common way that we're going to use the ideal gas law in order to do our work. Is we're going to pick and choose our pieces and our parts, and we're going to figure out what we need to use and how we need to use it. So that's pretty much how that one goes out. Now, some ideas for you, some things that might make this easier for you. Tips, as it were. Make sure that you write down all your variables, okay? Take the time, do what I did, write your variables down so you know what you got. Make sure that you can see the pieces and the parts, or if you don't write them down, at least identify them inside the text so that you understand what's going on. Make sure that you convert your units to what they're supposed to be, or so that all units match. Okay, do what I did here. Get your volume into liters. Get your temperature into Kelvin. Make sure that you've got all those parts already done so that when you start putting them in here, you don't have to stop what you're doing to get that done. Okay. Rewrite your equation so that your variable of interest is by itself right there. So that was one of the first things I did. I always do that. Makes it easier for me. That way I don't have to do it later. Yeah. And then the last thing that I would say is always carry along your units so that you can use your dimensional analysis brain to make sure that you set it up correctly. If you carry your units along inside your calculation, you can see if you put the wrong number in the wrong place. If you don't carry your units along, you don't see that, and you don't necessarily have the assurances that you did it right. And so that's a very common mistake that people make. They put the wrong number in the wrong spot, and without that unit there to tell you that it's in the wrong spot, you just don't know. And that way you don't make any silly mistakes. Now, when we talk about relating the ideal gas equation and the gas laws, we can actually make yet another mathematical equation with this. And this is what we call the combined gas law. And when we're looking at these problems, if we have a single volume of gas that undergoes conditions other than or including pressure, volume, or temperature change, we can take all of those things and we can record those into one equation. So again, it's a closed system. If the number of moles aren't changing, we can use what we call the combined gas law to make this a little bit easier. And so the combined gas law actually is kind of cool. It is the pressure 1, volume 1 over T1 is going to equal the pressure 2, volume 2 over T2. And so this works because the number of moles are constant, and we also know that we're not exchanging pieces or parts anywhere else. And because we aren't having that, this takes all three of the gas laws and ideal gas law, and it kind of makes into one spot for us, which is really, really, really helpful. And so when we're doing that, we would want to use some hints to make sure that we're doing it. Make sure your temperature is in Kelvin. Make sure your pressure units and your volume units are the same. Okay. Yeah, just make sure that those match. So I'm going to erase some stuff, move this up so I got some writing space, and then we'll finish this up. So here we are. We're going to use an example of combined gas law, and then we can give this video a rest. So a balloon has a volume of 6 liters at sea level, which is 1 atmosphere of pressure, and it is allowed to ascend till its pressure is 0.45 atmospheres. The temperature changes from 22 degrees Celsius to negative 21 degrees Celsius at this time, or in this time. What is the new volume of the balloon after the change? All right, so that to me sounds like there's a whole bunch of before and after pressures, temperatures, and conditions, which probably lends itself to P1 V1 over T1 equals P2 V2 over T2. That's probably a combined gas law problem. Now, let's start looking at our pieces, let's start looking at our parts, and let's see if we have enough information to actually do this, okay? So a balloon has a volume of 6 liters. What is its new volume? Okay, so this is our V1. So I'm going to label that guy V1. It's got a pressure 1 at 1 atmosphere. So that's my pressure 1. I have a new pressure over here of 0.45 atmospheres. So that is my pressure 2. Okay. Temperature changes from 22 degrees Celsius to negative 21. So this number, the warmer temperature, is my T1, which makes sense, and my colder temperature is my T2. Okay, my question, what I'm trying to solve, is my V2. So V2 is equal to my question. So I have 5 out of the 6 pieces of information. 1, 2, 3, 4, 5. My 6th one is what I'm trying to solve for. So we have enough information to use combined gas law, and so that's what we're going to use. Now I want to get V2 by itself, okay? And so we're going to put V2 by itself. Now to do that, I'm going to multiply this side of the equation by T2, because that's going to cancel it out of there and cancel it there. What I do to one, I have to do to the other. So now it's in the numerator over there. I want to divide this mess by P2, so I'm going to put P2 down here. That's going to divide that out, and that means I have to put P2 over here. So when I redo it, V2 is going to equal temperature 2, pressure 1, volume 1, divided by pressure 2, temperature 1. Okay, so I have all my pieces. So that's good. So now we can set that up. Before we actually use this equation, though, we want to make sure that we have whatever things in the right units that we have to have them in. Okay. First thing I want to look at is my temperature. I didn't change temperature to Kelvin yet, so we got to do that first. So 22 degrees Celsius plus 273.15 K, just 1.5. This is my T1. So T1 is 290 something, 295? 295.15 K. 295.15 K. My temperature 2. This is going to be negative 21 degrees Celsius plus 273.15. That is going to be 252.15 K. Okay, so now we have our temperatures, so we can put those in. My pressure units are both in atmospheres, so I have atmospheres and atmospheres. I'm not going to change them because they already work. My volume unit is in liters, which means that'll work. So everything here should spit out a volume unit of liters when it's all said and done. We're going to carry along all of the units as we work in here, just to make sure that that's the case. But we'll see. All right, so here we go. So this mess is going to equal temperature 2, which is 252.15 K. Okay. Pressure 1. Pressure 1 is up here. That is 1 atmosphere. Sweet. Having a 1 in a calculation like this makes the math easier. Yay! Volume 1 is 6.0 liters. 6.0 liters. Okay, that's the numerator done. Let's make my sign. Pressure 2. Pressure 2 is way over here. It's 0.45 atmospheres. 0.45 atmospheres. And the last number is temperature 1, which is right here. It's 295.15 K. Okay, now let's think about this with our big brains here for a second. Now, this is a balloon at sea level being released and being allowed to go way up into the atmosphere. What do we think is going to happen to the volume? Do we think it's going to get bigger, or do we think it's going to shrink? And so, can we predict it? Can we predict what's going to happen and see what's going on? And I would say, if you look at it, just looking at our atmospheres, we're going to be dividing. So our atmosphere unit is going to end up getting bigger because this is half, roughly. This is not going to be roughly half. So I think it's going to get bigger. And I think that we're going to see a fairly large change. Okay, so you just got to be able to kind of look at it, roll at it, look at the math, and make sure that you know what you're doing or it makes some sense. Okay, so let's cancel units and make sure we set this up right. I have a Kelvin in the top. Gone. I have a Kelvin in the bottom. Gone. Okay, so units of Kelvin are gone. So that balances out. We have atmospheres here. We have atmospheres here. Those are both gone. The only unit left behind is that unit of liters, which is the volume, which is what we want, hanging out in the numerator by itself. And so that means that we're going to end up with a unit in volume just like we wanted it to. So that's good news. Okay. All right. Last thing we have to do is do the math, and then we're done. So 252.15 times 1 times 6, enter. Divide by, open parentheses, 0.45 times 295.15, close parenthesis. The number that I got was 11.39 liters. If we're going to be pedantic about it and we're going to round it to sig figs, it's going to be 11 with our sig figs considered. Okay, there we go. Now our volume just about doubled, which makes sense when we think about this 1 and the 0.45, and this isn't quite a half, so we did okay there. So I think that we're right. I think that that's all right. So that's combined gas law. That's how it works. The hardest part for a lot of folks is this part right here, is being able to walk it back and forth and being able to write your pieces and figure out what your formula is going to be when you're looking for a different variable. And that's not chemistry that makes it difficult. This is algebra, and that's sometimes the tools that we have to use are a challenge, and so we just got to kind of work our way through that. So thank you for your time. Take care.